Thank you for turning up for the in English we say the bitter end. Right to the end of the course. So what I will do this week is, first of all, tell you a little bit about shading for photovoltaic systems, because I said last week that shading is really the key issue for many photovoltaic systems, mainly ones that are in cities and are distributed rooftop solar, those sorts of projects. And I'll explain to you why shading is important and how you can minimize the effects of it. So that will be virtually everything to do in this current lecture, Lecture 9. And then after Lecture 9, I'm going to talk a little bit about the integration of intermittent renewable energy into an electricity grid. And that leads very naturally to the question of storage. So we'll finish off probably tomorrow with a few discussions of storage. Since we're quite a small class, please feel free to ask me questions either in the chat or raising your hand, because we have a sufficiently small class that will be easy to cope with. These slides that I'm going to show you now are actually prepared by a student of mine, and the student's name is Ken Anderson. So this is a student here. And he was one of the engineering students at the University of Calgary that designed and built this small house with the photovoltaic system on the front. You've seen at least 2 other photographs of this system. And one of the values of the system is that the modules have the same inclination, but have variable azimuths. And I've used that variation in the azimuth to give you an indication of how important that can be to the production from a PV module. And you can see here from this slide, or this photo, probably more clearly than the other photos that I've shown you, that the inclination of these modules is somewhere around about 40 degrees, which is a good angle for latitudes like Calgary's and Novosibirsk. So Ken's slides on shading. You've already seen this slide because this was a slide that I showed you last week, talking about the current voltage curve for photovoltaic systems, and then also the power voltage curves, and pointing out that the maximum power point for a PV module is usually a pretty steep or pretty well-defined maximum power point, and that point can change very much dependent on the solar radiation that is seen by the cell, and to a lesser extent any changes in the cell temperature. And I'm not going to talk in detail about maximum power point tracking for photovoltaics, because the techniques that are used are actually very similar to what I've told you about for wind turbines. Okay. So let's have a look at a typical PV photovoltaic modules. And these slides are a little bit old now. They're about 7 or 8 years old. So the number of cells in the module is probably less than what we would have nowadays. But the basic principles of what Ken is showing you here apply to any photovoltaic module. And I've already pointed out to you that a PV module consists of a number of cells, and for the simple reason that the voltage produced by a PV cell is quite small. It's usually only about 0.6 of a volt as the open circuit voltage. So if we want to get a reasonable voltage out of a PV module, then the cells have to be arranged in series. And there you can see a typical series connection between the solar cells in a PV module. And it doesn't really matter whether it's 60 cells in the module or 72, it will be a series connection like that. Okay, I'm not going to say anything more about this data sheet for the particular PV modules that Ken used for his analysis. This has virtually the same information that we looked at in a previous lecture when we looked at a more modern PV module, but it might be useful to you if you review the slides after the lecture just to get an idea where some of the numbers that I'm going to quote in the following slides actually come from. Okay, so let's do what physicists love doing, and that's have a thought experiment. So let's imagine that this PV module is in bright sunshine, but for some reason, and it doesn't really matter why, one cell in that module is shaded. What happens? Basically, because the connection is a series connection, the whole module has stopped producing power because the current can't go through the shaded module, and therefore it is blocked from going through the module, period. There's also an issue that I haven't talked about before, which is a very important one. Fortunately, it's a problem that has a fairly easy solution that I'll show you in a few moments. Not only do you lose the power produced by the module, you also produce what's called a reverse bias on the shaded cell. So the voltage at the top end of the cell will be 44, because that's the number of cells ahead of this particular cell, times the open circuit voltage, which is 0.6 of a volt, and we get minus 26.4. The voltage at the other side, by a similar calculation, is plus 9. And if you look at the combination of those, that gives a voltage across the shaded cell of minus 35.4. And that is much higher than is needed to actually destroy the cell in that PV module. So not only does shading not only does shading of one cell stop the whole module from producing power, it actually causes danger to the cell. The solution is very simple. You can see the solution up the top there. We have bypass diodes. Okay, so 1, 2, 3 bypass diodes. And that is by now sort of generic standard operating procedure for PV modules. And the reason, of course, is that if this cell here, say, is shaded, then that will produce any current flowing in these two columns of cells, but it will still allow the current to flow in the other cells, and will also prevent reverse bias occurring on that cell, because it's part of a string of cells, if you like, that is not long enough to get reverse bias. So the idea of the bypass diodes is to bypass the shaded cells, to protect those cells, and also allow any unshaded cells to produce power. Now, it may turn out that the whole module is shaded. Obviously, then there would be no power produced anyway. So there's just a quick demonstration of what you would think is the obvious thing. So instead of shutting down the whole module, the shaded cell now has shut down only 1/3 the module. So this arrangement, usually with 3 bypass diodes, is very common. And I think it's the reason why it used to be the standard layout that PV modules had 60 cells. The newer ones have 72. And I think the fact that 72 is divisible by 6 is part of the reason for that, because even with 72 cells in a module, you can still get by with 3 bypass diodes. And there are fancier arrangements for the bypass diodes. Some PV modules will have more diodes at the bottom of the module, because it's often the extremes of a module that gets shaded. But what you see here is pretty much the most common arrangement in a PV module. Okay, so we talk about sub-modules, and each of those sub-modules is controlled by a bypass diode whose job it is to shut down any sub-module that has enough shading on it to not be producing any power. And that is, as I said, a very simple method by which you can protect the module and the cells, but also allow at least some of the module to operate. Then what happens, of course, is that, as I've noted a number of times before, modules are often connected in a string, which is usually a series connection of modules, and then sometimes strings are connected in parallel. Okay, what you see here is the most common arrangement, particularly on a larger PV system. And if it's a large system, then there's usually one inverter for a large number of modules. And I want you to remember, as we go through the example calculation on shading that I'm about to do, that this is the case, the worst possible case, when you have a single inverter operating a large number of modules. Okay, so back to the situation that I showed you this photograph at the beginning of the lecture last time. There is one inverter for the whole array. There's 4 strings in parallel. So 1, 2, 3, 4. And if you remember, and you can probably just see it on this photograph here, you can see the shaded area is down the bottom of string number 4. So there's 2.4% of the area is shaded, and we're going to do a simple calculation to see how much power that it loses from the whole array. So the shadow spans 3 modules or 7 submodules. So each of those submodules will be shut down by the bypass diodes. So the shading will cause the modules indicated by the red area to be bypassed and not produce any power. So the open circuit voltage of this string drops. And if you look at the performance curve for this string, which is just 60 or however many cells multiplied by the curve for a cell, we have the voltage current curve at the top and the power voltage curve down there. And clearly the maximum power point is here, which is 2,600 watts. So if those 13 modules were in series and they were in complete sunlight and there was no shading, we would be getting 1,600 watts out of that module if the solar radiation level was 1,000 watts per square meter. So this particular installation has 4 strings in parallel. So putting the strings in parallel will just move us up the current voltage curve. And so what you see in green here is the maximum power point for the 4 unshaded strings in parallel. So 10.4 kilowatts. Now, if we have shading on the string, then that reduces the voltage for the same current. Okay, and that changes the maximum power point because the single inverter is now trying to maximize the sum of 3 unshaded strings and 1 shaded string. And so you can think of the shaded string as dragging down the performance of the unshaded strings. And if you do the calculations, you can see from the manufacturer's specifications, it's very easy to determine that with partial shading, we get less than 9 kilowatts compared to an unshaded value of 10.4 kilowatts. And if you do the calculation, that's nearly a 14% loss. So we have 2.4% of the shaded area produces 14% loss of power. So there, in a very simple explanation, is the way in which shading affects the performance of a PV system. Okay, so how do we get around it? How do we avoid losing that 14% power for 4% shading? Okay, the main answer is to go away from centralized inverters. Okay, remember, this calculation was done for a single inverter controlling the whole array. That we have 4 substrings, and if we redid the analysis by saying having 1 inverter for each substring, then the loss would come down substantially. I don't remember exactly what it would be. If we go to the extreme and have a single inverter for each module, that would minimize the loss. Okay, it wouldn't bring it down to the area shaded, but it would bring it down in percentage terms to the area of the substrings that are shut down by the shading. And that would be significantly less than a 14% loss. Okay, so that is the main reason why there are different inverter technologies for photovoltaic systems. If you're going to have a system where there's no shading whatsoever, and that's a very common situation, or minimal shading, then you go for the cheapest power electronics possible, which is normally a centralized inverter. If you're going to put a system on your rooftop where you may get shading from street lamps or chimneys or other parts of the roof, or your neighbour's house who's just built a second story, then you need to go with power optimizers or microinverters. Okay, so here's a couple of examples of large solar farms. In the context of what we're talking about here, the example is important to show you that there's virtually no shading on this. Okay, there can be shading from one PV array to the one behind it, and you can see some examples here where that occurs. That's likely to occur usually only in midwinter, when the sun is very low in the sky, or sometimes when the sun is rising or setting. That is called self-shading. And of course, that is extremely difficult to avoid, because the only way that you can avoid any self-shading is to have the PV modules spaced so far apart that it's going to cost you a lot to lease the land to put your solar farm on. You know, the further apart or the farther apart these arrays are, the more expensive will be the rent for that land. But apart from the self-shading, it's very, very unusual for a solar farm to have any trees in or any other things in the proximity to the farm that are going to cause shading of the PV modules. So this is a 17 megawatt PV array. It's actually in southern Alberta. It was installed in 2018. And as far as I know, it's still the largest solar farm in Alberta, although there are plans to build much bigger ones, but I don't know where they are in terms of construction. So what I was telling you about in terms of shading is usually more of an issue for installations where trees, rooftops, etc., are going to be prominent. Okay, and the last thing to show you for this slide is an example of what's called a bifacial PV module. This is another installation in Canada, and if you look at the back of the PV system, so the back of the modules is shown in the top photograph and the one on the right, compared to looking at the front of the modules on the bottom left, you can see that the back of the modules also have PV cells. So a bifacial module is one that has PV cells on the front of the module and on the back of the module. If this was a conventional module, you would just see the usually white backing sheet for the PV module. And the idea of bifacial modules, you can probably get an idea from this photograph here with lots of snow around. The idea is that they can capture the reflected radiation from the snow and other causes, usually in wintertime. And so they're held to be very suitable for cold climates like Russia's and Canada because they allow an increase in PV production in wintertime, which is typically the time of the year that PV production is naturally very low. Whether they are actually cost effective or even do give a substantial increase in performance, we don't really know yet. Because it's a relatively new technology. This PV installation was only finished this year. It was finished this summer. And there hasn't been enough operational data from the PV system in order to judge whether the small extra cost of bifacial modules, they cost about 5% more than a standard module, whether that extra cost is recouped in terms of increased power output. So maybe if I get to go to Novosibirsk next year, which I'm very much hoping to do, we might have some updated information and I can let you know. Okay, so that's pretty much all I wanted to say about PV systems. I'm not going to go through these points here, which are sort of just a collection of random thoughts, more or less, on PV systems. The only thing I wanted to pay a little bit of attention to is that I haven't said anything about tracking systems. Okay, tracking systems can be either one axis or two axis. If they're two axis, then they allow the module to face the sun at any hour of any day of the year. If you do the calculations for Calgary, and if you're interested in tracking, you can do these calculations using SAM. You will see that for latitudes like ours, tracking will give you something like 40% more electricity output. But then the question is that extra electricity worth the extra time and effort to put into a tracking system? And if you talk to people in the photovoltaics industry, most of them say no. And they say no for the reason that PV technology is very robust. Okay, it lasts a long time. I pointed out in a lecture last week when we looked at the manufacturer's specifications for a PV module. All PV modules nowadays are guaranteed for 20 or 25 years. And you'll find also that the power electronics that you buy for a PV system are also guaranteed for that length of time. That's an extraordinary guarantee. I don't know of any other commercial product that is guaranteed by the manufacturer to that level. So if you build a PV system, as long as you look after it reasonably well, and it doesn't take very much, you have to clean the dirt off the front of the modules and you have to check the system performance in case you've got a few usually minor problems with the power electronics and the modules. It's going to last you for 20 years. So what the PV people tell me is why, if you've got a technology that has lasted so long, why combine it with a mechanical tracking system that's going to have a lot of maintenance and probably won't last anything like 20 years? And so, the argument is simply, mount the modules straight onto a frame like you see here, don't worry about tracking because it's not worth the extra cost and maintenance for the extra electricity. Okay, so that's a very quick and probably as good as you need to understand a little bit about effects of shading on PV. So now I come to...
I want to ask one question.
Yes, sure.
When you demonstrate Brooks solar farm, it's interesting that some solar cells was in shadow of each other.
Yes. So, usually that happens either at sunrise or sunset. Okay, or probably that photograph was taken in the middle of winter, so the sun was very low in the sky. Okay. It's almost impossible to stop one module shading another. Okay. And the only way you can do it is to move them farther and farther apart. And the problem with that is that you need more and more land for your PV system. And so
it's optimum. Okay.
Yeah, so your rent or your lease payments get higher. Okay, are there any other questions on PV and shading? Because we're actually going to leave PV systems now, and I'm going to talk a little bit today. I'll probably get through most of this slide today, and tomorrow, I've got just a few slides on some of the storage technologies that I'm familiar with. So we're going to look at the question of high penetration of renewable energy. So the key issue with high penetration of renewable energy is how do we deal with intermittency? I've already given you right at the beginning of the course some pretty graphic or pretty detailed information that documents the intermittency of a renewable energy system. And I'm going to show you some of that information again. And as we go through this lecture, let me point out, or let me refresh your minds. I've talked a little bit about penetration. It has a formal definition, and that formal definition is usually given as the total renewable capacity divided by the average grid demand. And remember also that the capacity factor is the rated power output is the average power output versus rated capacity. And we saw for wind farms, typically 30 to 40% capacity factor. For solar PV, less than 20% normally. So if you combine high penetration with those sorts of capacity factors, that means that you're going to have renewable energy generation on your electricity grid that sometimes can produce much, much more power than the grid needs to, or the grid demand. Okay, because if you have, say, 100% penetration with a capacity factor of 40%, that means that at sometimes you're going to be capable of producing nearly twice as much power as the grid needs. Okay, so that's a particular issue about high levels of renewable energy in an electricity grid that is related to the fact that for most renewable technologies, the capacity factor is relatively low. So let's have a look at some examples again. I've shown you this example before, and there's nothing special about it. It's just that I happened to get this information. This is for 10 days in July 2011 for Alberta, actually. And the blue shows the total grid demand, and the green shows the total wind power. And you need to multiply the blue curve in your head by a factor of 10. I've scaled the total grid power down by a factor of 10 simply so I could plot it on the same figure. Okay, so three things to notice. One is that the wind power production can ramp down and ramp up very rapidly. And these are the events that the electricity system operator dreads, because when the wind power is ramping up, the system operator has to tell the other generators to shut down. And similarly, when the wind power is ramping down, the system operator has to tell the other generators to ramp up. Okay, and that is often a difficult thing to do. If you do the mental multiplication by 10, you can appreciate that in July 2011, those problems of intermittency were probably not major problems. There are, relatively speaking, substantial ramps up and down. There is substantial lack of correlation between the wind power production and the grid demand. But if the wind power is sitting at around 5 to 10% penetration, nobody's going to be too concerned about it. However, imagine if we magically increase the wind power production by a factor of 10. Okay, so that these graphs were relatively correct. Then you can imagine that the issues of intermittency become extremely important. Okay. How do we deal with intermittency? There's actually quite a number of ways of doing it. And I'm going to give you later on in this lecture an example of an electricity grid that has the highest penetration of wind power in the world, but has no storage on it. Okay, because storage is a very important technology, but it's only one of the possible technologies that can be used to deal with intermittency. One of the most important ones is geographical dispersion, okay, which simply means spread your renewable energy generators over as wide an area as possible. And here's an example from California. This was done by my former PhD student, Hamid Shakir, as part of his PhD project. So what he found, as you would expect, as you go from a single site through a neighborhood of a city to the whole state, and this is in California, so there's about 30 million people here, and there's actually a total of something like 80,000 PV systems that he aggregated to get the total PV output. You can see that as you go down or up in granularity, the smoothness of the production gets greater. Okay, so as we aggregate the production over a larger region, both the PV power is more predictable, and I'm going to talk a little bit about forecasting in a moment, and it's also smoother. Okay, so the system operator, provided they have a good idea that this is the power that they're going to get, they're not going to have to worry too much about ramps, except for a reason that I'm going to come back to later on. So geographic dispersion is actually one of the best ways of dealing with intermittency. And that's been done in Germany to a large extent. The north part of Germany is considerably windier than the southern part of Germany, but there are a significant number of wind turbines in southern Germany. And part of the reason for that is that helps to give the geographic dispersion of wind power over the country. I didn't point out, and this is a good time to do that now, one of the problems that we have in southern Alberta is that most of our wind farms are in a very small area. Okay, so we get very little benefit of geographic dispersion, and that's one of the reasons why the ramping up and the ramping down in wind power is so clear in this data. Okay, here's a very famous example. This is California. And California is interesting because it is a system that has the highest number of distributed photovoltaic systems on the grid. So what we see here is the development of PV capacity over time. So yellow is the accumulated installation to the year before. So the yellow block here is the installation to the end of 2020, and the blue on the top is the installation that year. And you can see here that the data that is used here comes from over 800,000 rooftop solar projects. It's actually the best information that I have is that there's over 1 million rooftop solar systems in California. So that's really good for some reason. That's a lot of renewable energy getting generated, but it does have its downside. And the most important downside is shown in this figure down here. And if you haven't seen this curve before, welcome to it. This is a very famous curve. It's called the California duck curve. So there's some duck hunting in California. And it's called the duck curve because it supposedly looks like a duck. I'm not sure whether that's true or not. But what we see here is the total grid demand versus hour of the day. And the difference between this grey line here is the total grid demand versus hour of the day. And what you see down here is what's called the net production. That is this demand here minus the PV production. So think of a very common situation in California. Okay, it's a very hot summer's day, and California has a lot of sunshine and it has a lot of hot weather. It is very hot. People put their air conditioners on. Right? And there's a lot of PV production, okay, because a hot summer's day usually correlates very well with PV production. In other words, and in fact, there's almost a perfect correlation between the electricity demand and the PV production. So there's no intermittency. It's entirely predictable, right? But the problem is, what happens when the sun sets? Okay, so somewhere after 3 p.m. Onwards, the sun is setting or the PV systems are getting shaded because the sun is low in the sky. The PV production drops off, and it drops off incredibly rapidly. Look at this, 13 gigawatts in 3 hours. So the system operator has to have that amount of power in reserve, and the system operator has to be able to bring that power online quickly enough to trade off against the reduced power from the PV systems. So it's a very famous example, and it's a unique problem that electricity systems are facing now that, those systems that have a large amount of distributed power. And I don't think they're necessarily problems that could have been easily predicted before renewable energy took off. Okay. This is done in the context of PV. It's from a publication by an author that's done a lot of work on modelling PV production. But it talks a little bit about some of the techniques that can be used to reduce intermittency effects. I've already talked about geographical dispersion. And his graph here is very similar to the one that I showed. So imagine our basic case is that here's our PV output here, here's our load demand. Load is typically below the PV production during the sunny part of the day and clearly above it in the nighttime. Storage. obvious one to do. So when you're producing a lot of power, save some of that power in batteries, in pump storage, hydros, other storage systems, and then feed it back to the system at night. Storage at the moment usually only works on a short time scale. Okay, store during the day, use at night is often the best way to use storage. However, if you have climates like ours, you may need longer term storage. I'm working on I think I might have told you, I'm working on a project with the Arctic Institute of North America, who has a research station up in North Canada. And they have a PV system. Even though it's way up in North Canada, they have a PV system which produces a lot of power in summer, because at the peak of summer, they get nearly 24 hours of daylight. However, of course, it produces nothing for at least a month or two in winter. And they're looking at how you can produce power in summer, store the power, and use it in winter. And that is actually hard. Batteries are not particularly good for doing that, because they will self-discharge over time. There's no hydro system available to them, so they can't use pump storage hydro. What they're thinking of doing is manufacturing hydrogen in summer by electrolysis from the PV cells, storing that hydrogen and then running it through fuel cells in wintertime. And that's just a very, very brief introduction to the role of hydrogen in future energy systems, because I think you people will find that it's going to play a huge role in energy systems of the future, partly because Russia has so much gas. And one of the possibly the best ways to use that gas in a renewable way is to reform it into hydrogen and capture the carbon that is produced in that process and store it underground. So I'm confident that in the next 20 or 30 years, Russia will be one of the world's leaders in hydrogen production. The other fascinating thing about hydrogen is that it brings the electricity system into other energy systems, because hydrogen can be produced by renewable means, electrolysis, say from excess wind power or PV power, but it can also be used to fuel transport. Trucks and cars and trains can run on hydrogen. Aircraft possibly will be able to run on hydrogen. So hydrogen is going to be a big part of you people's future. Unfortunately, I didn't have enough time to talk about it to the extent that I think is worthwhile. So storage has issues both of the timescale of it and the amount of storage. The other thing that you can do is what's called curtailment. Okay, and that is simply to say, when the renewable energy production is too high, just shut it down. And that's pretty easy to do for PV. It's not quite so easy to do for wind turbines. And of course, the people who own the solar farms or the wind farms or the rooftop systems, they don't want to do this because they're losing power. But one of the other possibilities could be, instead of actually shutting down the electricity production, if the renewable production is too much, that renewable production can be sidetracked to produce hydrogen. So hydrogen actually comes up as a very, very promising way of optimizing the use of renewable energy. The other important tool is forecasting. Okay, the California duck curve aside, virtually every time you have a problem with intermittency, if you can predict when that problem is going to happen, it's going to be less important in magnitude. The problem with that is that renewable energy production is very difficult to predict. Here's some examples here. I've got two examples that I'm going to show you. First one is from Alberta for a month in 2016. And what you see in orange is the predicted wind power output. And what you see in green is the actual wind power output. And the grey area is sort of the plus or minus a standard deviation or so. And you can see that there are some times, like here, where the prediction does very well, and there are other times when it's wrong by a factor of 2. Okay, there's an enormous amount of research going on to improve the prediction of wind power and solar power, because for climates that have a significant amount of clouds, predicting solar power can be as difficult as predicting wind power. It's not easy to do, and it's not a technique that can be relied upon to deal with a lot of the important issues. Because if you're using wind power to predict your wind ramps, for example, you'd get some of them right, but you will get some of them probably wrong enough that you would crash your electricity grid. And here's another example from Australia that I was looking at recently. This shows at the top here, black is the actual power production over, I forgot to look at how many days this is, over 1 day. And the solid red is a 24-hour ahead forecast, then the 8-hour ahead forecast, and the 1 hour ahead forecast. And if you look through the errors on the bottom of the graph here, you can see that, as you would expect, reducing the forecasting horizon improves the accuracy of the prediction, but there are still situations where even the 1 hour ahead forecast is just plain wrong and can't be relied on. My personal feeling, this is an area that I actually do some work in. I work with colleagues in Calgary looking at the prediction of wind power in the future in Alberta. My view is that we're not going to avoid these sorts of errors that you see here for a long, long time, if ever. I think we'll be able to reduce the errors, but I think in some sense we're dealing with an inherently chaotic situation that you're not going to get the errors down to zero. Certainly anytime soon. Okay, I'm going to look at I've looked at California as one aspect of rooftop solar in California. That is a system that has a high penetration of renewable energy. Here is another example of a high penetration of renewable energy. This is Denmark. And what you can see here in the brown at the top is the actual production versus time. And here we see 1, 2, 3, 4 and a bit days. And you see both the onshore wind production at the top and the offshore wind production. And again, as we saw from the Alberta data earlier, there's huge variations day to day, or what would that be, 4 hours to 4 hours. But there are certainly times when the total renewable energy production exceeds the electricity demand. So here's a question for you. How does Denmark deal with that problem? Because Denmark has the highest penetration of wind energy in the world. It's over 50% at the moment. It has no significant storage facilities. How does it deal with intermittency? There. It deals with intermittency by having very good neighbours. Okay, so Denmark has interties with Norway, and Norway has a lot of hydropower, because the other side of sometimes producing too much wind power is that there's going to be a lot of times, like here and here, where you're producing far too little. And so at times like that, the Norwegian owners of the hydro the hydro plants in Norway make a lot of money by selling electricity to Denmark. Denmark has very good interties with Sweden, with Germany, and through Germany to Eastern Europe. And so when Denmark produces too much power, here's an example of producing 140% of what it needs, all it does is simply offload that excess power to its neighbours. So that's a little bit like the effects of geographic dispersion, because you would think if there's a lot of wind being produced in Denmark, if you go sufficiently far away from Denmark, the wind power is probably quite low. And as I said, Denmark doesn't have any storage. So it's not necessarily the case that high penetration of renewable energy requires storage. Here's a really interesting situation that I've only just come across, because last week I attended a seminar that was run by the International Solar Energy Society, and they were talking about high penetration renewable energy and electricity grids. And one of the speakers was from Australia, where I come from, but I didn't know the situation in Australia. What you see here is what they call the underlying demand. And compared to that underlying demand is the percentage of solar and wind penetration. And this is actually only for part of the Australian electricity system. It's not for the total system. And what you see in grey is actual data from 2019. And what you see in red and yellow are predictions to 2025 that have been carried out by the Australian electricity system operator. And that's made them extremely worried, because what they're finding is that quite a number of the scenarios by 2025, which is not all that far away, there's going to be more solar and wind power produced than necessarily can be absorbed by the grid. Australia can't export power to New Zealand or New Guinea or anywhere like that, so we don't have Denmark's options there. But this is the outcome. I didn't realise it till I went to the seminar. There's so much rooftop solar in southeastern Australia that the rooftop solar on its own has more than 100% penetration. So the rooftop solar, the distributed solar, can actually produce more power than the grid demands. That suggests some very fascinating issues. One of them, which occurred to me, unfortunately, I had to leave the seminar before the end, so I couldn't ask a question. If you have a large amount of your power produced by distributed solar, how do you know how much power you're producing? Okay, you don't. If your power is produced by a wind farm or a solar farm or a coal-fired power station or a battery system, then those producers or those generators have to tell you how much power they are producing, and you know how much they're producing. But all those million rooftops in California, or percentage-wise, probably this more in Australia, they don't have to tell the system operator how much power they're producing. Unfortunately, I didn't get a chance to ask that question, but I'll try and follow it up. The other problem that this causes, and the problem happens in California as well, it hasn't got to a particularly bad state in California. The main thing that they're worried about in California are the high ramp rates that are associated with this. But what's happening in Australia is that the net demand is proportionally much less than it is for California. And what that means is that the generators that are available to the electricity system have a number of very significant disadvantages. They don't have any physical inertia in them. And electricity system operators, being very conservative people, they love inertia, because inertia is a very simple mechanical feature of a system that helps to keep it stable. If you have a voltage drop or a frequency drop in a system, then the inertia that you would get in, say, the large gas turbines that are driving an electricity generator, they will slightly slow down in response to that and keep the system stable. If you have a whole bunch of producers like rooftop solar that has no inertia, then you've got a much more difficult system to keep stable. And these are some of the issues that the electricity system operators are now starting to face as some electricity grids in the world are moving towards a position of having 100% penetration of renewable energy. So the message that I'd like you to take home from that is that it's a challenging task. There's a lot of very intelligent engineers and scientists that actually get employed handling these problems. It can be done, but it's not easy. I sometimes think that running an electricity system is the hardest job a human being can have. So, okay, we're going to finish on this slide for tonight. This is leading into a little bit of a talk about storage for tomorrow. And if you look for any information on storage, and I've taken this from, it's getting fairly old now. It was updated in 2016. So, but it's a technology field that is changing. A lot of it is changing very rapidly. What you often see when you get information on storage is a plot of discharge time versus power ratings. How much power can you store and how long can you deliver that power for? And so you look at some very newsworthy or well-known technologies like batteries and fuel cells. They're pretty modest in their capability in terms of how long they can provide the power for and how much power they can produce. And the other point to make is, of course, that this graph ends at hours. So if you have a problem like the Arctic Institute of North America that I told you about earlier, that is a question of seasonal storage, right? Then virtually none of these technologies are going to help you. Okay. What I find fascinating about this curve is what's happening over here. Look at large scale, what they call bulk power management. Lots of time at lots of power. And a big electricity system with a high penetration of renewable energy probably needs some of these technologies. And what we see here is we're very limited in technologies. We can use pumped storage hydro, and I'll tell you a little bit about pumped storage hydro tomorrow, or we can use this technology here, which stands for compressed air energy storage. Okay, compressed air energy storage basically means compressing air and storing it underground. So it's a little bit like carbon capture and storage, except with the compressed air, it's released and it's run through turbines to produce power. So, but these are pretty much the only technologies that are available that allow a lot of power to be stored for a long time. All the other technologies that you've probably heard a lot about, like lithium-ion batteries, supercapacitors, flywheels, which are a very interesting technology because they respond very rapidly, they're down in the middle of this chart here. And I think it's important to recognise that. And I think with that, that's the end of that lecture. So I will stop sharing and we've just about finished. There's enough time. If anybody has a question or two, we could address that. Well, remember, tomorrow is your last chance to ask questions. So I encourage you to do it, and feel free to email me if you would rather contact me that way. I would be very happy to get any email questions from you as well. Okay. In that case, let's finish for today and come back tomorrow for the final meeting of this class. So I look forward to seeing you then. Bye.
Thank you. Bye-bye.